All right, thank you for having me all the way from New Jersey. Yeah, I'm going to be telling you about this paper that we put out in October. It's maybe a bit different from the other talks in that I'm not going to be talking at all about stabilizer codes. Yeah, and it was done with these, let me make sure that this works. Okay, yeah, with these four lovely humans. And yeah, all right. So to provide some motivation for this work, okay, I don't need to convince anyone that we need to do quantum error correction in order to like protect quantum devices from noise. But I want to sort of present this in a slightly different way, which is that thinking about an error threshold as being like a phase transition in like a statistical mechanics model. From the perspective that you have a certain family of codes, let's say surface codes. The family is increasing system size, and under certain noise models, let's say bit flip errors, there's going to be a sharp threshold. So like in the limit of system size goes to infinity, there'll be a sharp threshold below which information can be stored and decoded. And so you basically just have the usual sort of some parameter p tuning your noise, and there's going to be some transition between what I'll call a coding phase and a non-coding phase. In the StatMech community, there's maybe sort of two different perspectives that you can take on this error threshold. So the first is that it's sort of from the perspective of an algorithm. So you ask yourself, like, when could some decoder, it could be like a hypothetical, like optimal decoder, or it could be a more practical decoder, like minimum weight perfect matching or something. But when can that decoder recover the encoded information? And it can do that up to some threshold PC. And oftentimes you can map the performance of that decoder onto some classical spin model, and which has like quench disorder. And this algorithmic threshold will manifest as a transition in that spin model. And this has been this perspective has been around ever since like Dennis et al. In 2002. More recently, people have been looking at these error thresholds from the perspective of, rather than forget about the decoder, just ask, is there some sort of intrinsic transition within the mixed state that is produced by the noise channel? So I feed in some noiseless state, I act with decoherence, I get out some mixed state, and often there'll be some singularity in the entanglement structure of that state. So recently there's been works on, say, looking at Markov length, separability, or in topological codes you can look at various signatures of topological order. And what's been generally found is that this mixed state phase transition will coincide with the algorithmic threshold defined by the optimal decoder. So in this work, we were studying these mixed state phase transitions of a particular class of very unstructured codes, which are Haar-random codes. So the setup is as follows. Basically, I'm going to take k physical or k logical qudits and encode them into n physical qudits by applying a Haar-random isometry, which you can basically think of as I'm taking like my code words that are like say I have a I got something pointing straight up on the block sphere, and then I sort of just like randomize it so that like the Haar measure is uniform over the block sphere. Then I'm going to, and so that's going to be my encoding channel. Then I'm going to apply errors, such as like some form of decoherence, which I'll describe momentarily. And then I'm going to ask, when is the quantum information in principle recoverable? So like under a hypothetical decoder. It turns out that the answer to this question was answered by sort of two papers that were posted on the same day. This was like the week of the QIP deadline. So actually, if people who are at QIP might have heard, I think there was a talk about the second paper, but I'm going to be telling you about, well, the one that I wrote. And you can ask me later about like some differences between the two works, but all right. So yeah, in the rest of this talk, I want to basically break down the words in the title of my talk. So I'm going to give a little bit more detail on what I mean by a Haar-random code, and then I'm going to sort of look at the spectrum of the state that's produced by this code after feeding it through a channel. And then I'll tell you about the resulting transitions you get as a function of the error rate, and then I'll provide some outlook in future directions. And feel free to stop me at any time if you're confused or have a critique or something, anything. All right, so introduction. Okay, so here's the setup. As I said before, we're going to encode k-qudits into n-qudits via a Haar-random isometry. What I mean by a Haar-random isometry is perhaps easiest to think of in the setting where you purify the code. So you imagine that I have these k-qudits, so I'm going to purify that using putting them in k bell pairs with some reference r. And then I have a remaining n minus k qudits, which is just fed in some pure state, say 0. Then I take the part that comprises my system, so these k halves of the bell pairs and then the remaining ancillary qudits, and I apply a Haar-random unitary U, and that produces this pure state on the system plus reference, psi rq. And rho q is just the density matrix on the system, so it's just tracing out the reference. And that's going to be, equal weight on the q to the k code words, where q is the on-site Hilbert space dimension. Right, so that's my pristine encoded state, rho q. Now I'm going to apply errors. And for the purposes of this work, we focus on IID depolarizing noise. So it's shown schematically here. It's schematic because really there should be, noise channel coupling the bra and the ket, but I'm just showing it in 2D. Right, so you imagine each qudit of the system is fed through this single-qubit depolarizing noise channel, which you can write as this. So the key point is that there's some probability that the qudit suffers no error. That probability is going to be 1 minus p. And then the remaining probability, there's an equal likelihood of any arbitrary single-qudit Pauli error. So each of them has p over q squared minus 1. The key property of these Pauli errors is that they are, the Pauli group, they're pairwise orthogonal under the trace. So this property here is going to be somewhat important. Right, so that's the channel on a single qudit, and then we just take the tensor product of across the entire system. And then finally, we want to ask, okay, we've applied this noisy channel. Now, when can we recover the information? Spoiler alert, I'm not going to talk at all about actual decoding in this talk. I'm going to say when, hypothetically, is the information still there that could be decoded. And the way to probe that is via the coherent information, which is the difference between the entropy on the noisy system minus the noisy system plus reference. Sort of this ranges from plus k when all the information is still there to minus k when all the information has been lost to the environment. Just a note, I'm going to be putting these von Neumann entropies in units of taking all logs base q. So it ranges from k to minus k. And also as a helpful shorthand, whenever I put a little twiddle over the state, that means the channel acted on that state. All right, so this is going to be our probe of the phase transition, is this quantity here, and now we want to know how are we going to compute this, and how can we understand how this transition occurs? And the basic intuition for this is very simple. It's just that basically, if you take a code word and you act with two different Pauli errors on it, then you will get basically nearly orthogonal states. So basically, in other words, you start with two arbitrary code words, you act with two arbitrary errors, the overlap will be exponentially small, like q to the minus n over 2. And so you might think, okay, like, you might think two things. First, you might think this looks kind of like a nil-Laflamme condition, right? Like if this was 0 on the right-hand side. And the other thing you might think, if you were very naive, would be like, they're almost orthogonal, so like, I'm good, I can decode. But obviously, there's also exponentially many errors that can occur. And so the transition is just going to occur, or is going to be mediated by the fact that eventually that exponential number of errors will overwhelm this exponentially small overlap. All right, so to probe this a little, or a nice way to probe this coherent information and to calculate it is by decomposing the depolarizing channel in a slightly different way. So basically, before I wrote it as a tensor product over the single-qudit depolarizing channels, but I can also write the whole big thing as a sort of a convex sum over these other channels, n superscript w. And what n superscript w is basically it's a channel where I only apply errors of a fixed weight. So I collect all the possible Pauli strings that have weight w, where weight is just the number of non-identities in that Pauli string. There will be some large multiplicity of such errors, which I'll denote by omega of w. And so I can sort of package those all together into this NW channel. And then the total probability of having one of those errors that has that particular weight is just given by this binomial factor, which just takes this simple form here. And so the key point is that there's a sort of a binomial distribution of errors going from weight 0 up to weight n. And crucially, because it's just like a binomial distribution, when I say like typical error, what I mean is just like the peak of that binomial, which will be at p times n. Right. So I say that like, it's peaked at p times n. So I'm going to do something maybe a bit absurd, which is I'm going to say, let's imagine a world in which my channel is, it only applies errors of weight w. This might seem like super unphysical, but it's very convenient to study, and we'll use the insights from this channel to understand what happens when we go back to the depolarizing channel. Right, and so that's just precisely just this channel NW. I call it here the fixed error weight ensemble, but I will probably slip up at some point and call it the microcanonical channel. And the reason why I do that is because that's how I view it, is that this is basically serving like a microcanonical ensemble. So if you think of the depolarizing channel being like a canonical ensemble where it's got sort of quote unquote temperature tuned by this, this error rate p, and so it's got like peaked at some number of errors, but it's got a distribution. Then if that's the canonical ensemble, then the microcanonical ensemble is picking out, and so instead of fixing an error rate p, fixing quote unquote the energy, which is just the weight of the error. And so, under, you might think that these ensembles are going to be like equivalent. It turns out that's not quite true, but they will have transitions at the same point. And so, so we're going to start by studying this n superscript w. And we're going to do something very, again, absurd, which is we're going to construct an ansatz for what the spectrum is. And it turns out that the most naive thing that you can do actually pretty much gets it right. The naive thing is to say, at a given weight w, to first approximation, all of the non-zero eigenvalues are degenerate. there's basically two cases to consider. Either the total multiplicity of errors is smaller than the total Hilbert space dimension, in which case I can individually assign an eigenvalue to each different error, and there will be like enough room for all of those, right? So I can just think that my eigenvectors are just like code word acted on by each different error. So this is essentially treating that near orthogonal property that I showed before as being like as if it was exact. That's the one case. The other case is when there's too many errors. So omega of W is larger than the total Hilbert space dimension. Well, then we know that the total number of eigenvalues has to saturate at the total Hilbert space dimension. So basically, under this approximation that all the non-zero eigenvalues are degenerate, just the eigenvalue will just be 1 over the total number. And that gives you this very simple ansatz for what the entropy should be. And you can sort of apply very similar reasoning for rho RQ and rho Q. And basically what you find using this simple reasoning is, well, okay, you need one more thing, which is to say, okay, I'm comparing, let me go back. I'm comparing omega of W, like the total number of errors, to the Hilbert space dimension. And now I'm going to notice that in the limit of large system size, I can actually write this omega of W in terms of the entropy of the error distribution. So I fix W, and I say that W is equal to P times N. And what I'm saying here is just that the number of errors at that weight just goes like an exponential of this classical entropy. And that leads us to this very simple ansatz for what the coherent information will be, where basically it's pinned to the maximum that it could be as long as this entropy of the error distribution is less than 1 minus k over n. And then it has this regime where it's smoothly decreasing, and then it just saturates at the lowest possible value, minus k, at 1 plus k over n. This might look familiar to you, and that's because this threshold where it stops being maximum is precisely just the hashing bound. So saying that, this 1 minus k over n equal to the entropy. I've given this talk a few times, and I always like to point out that this is a very old result. It's older than I am. But I want to point out that it's somewhat new in the sense of this has previously been derived for the setting of non-degenerate stabilizer codes. Basically using very, very similar logic, the idea that you have total number of syndromes that you can give out, and if the number of errors is greater than that, then you can't decode. And that's basically what's happening here. However, I just want to emphasize that there's not really a way to make that reasoning rigorous in the sense of the fact that the threshold for a stabilizer code is at the hashing bound does not imply anything about the Haar-random code. Because this is not like stabilizer codes and Haar-random codes, or random stabilizer and random Haar-random will be the same for like a 2-copy quantity because it's like a 2 design, but this is not like a 2 replica thing. This is like the true von Neumann entropy. So 30 years later, we kind of have the result for Haar-random. All right. I do want to note that I told you this is sort of almost silly in how simple the ansatz for the eigenvalues is. And I just want to note that we actually have a better ansatz for what the eigenvalues are. Namely, we can argue and also observe numerically. So this, on the right-hand side, I'm showing the distribution of the eigenvalues for different microcanonical channels, like of different weights, for the largest system size that we could access, which was n equals 13. This is on qubits. And basically we find is, okay, it's not just a delta function, like they're not all degenerate. Instead, they follow what's called a Marchenko-Pastur distribution. The key point about this distribution Yeah, so actually if you look closely, you can see there's a dashed curve and a solid curve for each of these. And like the dash is the theoretical thing, and they match very well. The key property of this distribution, though, is just that there's a sort of, you can ask how wide is this distribution compared to its mean. And that ratio is basically controlled by the ratio of like these two numbers, the number of errors and the Hilbert space dimension. And so as long as you're like more than order 1 error away from the transition, this will actually still converge to a delta function. So this basically tells us that we can now look at the coherent information as a function of W, or W minus WC. And that transition, if we look at different system sizes, will collapse onto a single curve, meaning that the width of the transition is just like order 1 error. So like the correction to the ansatz that I wrote on the previous slide, like where it would be just like a sharp drop, the correction is just like in this narrow regime of like order 1 error. Yeah, and this is again numerics on qubits with a single, with k equals 1. All right, now you might be wondering, okay, I told you about this fictitious ensemble. Let's go back to the canonical ensemble and ask like what changes. And basically what changes is that now we instead of just having a single weight, we have like this distribution over weights. And so we're basically putting these, if we had, yeah, basically you can imagine that the most likely errors, or yeah, the individually most likely errors will be the lowest weight ones. So we're gonna assign those eigenvalues first. And then we go to the next, like, so we start with W equals 0, W equals 1, et cetera, and we just fill up the eigenvalues. Like with the total number of errors. And so that's these, and those will be like the distinguishable errors because they can each get their own eigenvalue. And these are like these, blue cups. And then eventually you don't have enough eigenvalues left to assign, and that's going to be the sort of what we'll call the reservoir, which is just like the stuff that's not distinguishable. So yeah, so maybe this conjures an image of, I don't know what the reservoirs are like in Australia, but I guess maybe in New Jersey they're polluted. So, so that's what you should imagine is happening above the hashing weight, so above WC. Those eigenvalues are just put into one big bucket that is not going to be decodable. We can actually look at this numerically. So basically, you can see at sufficiently low error rate, you have these very distinguished. So let me wait for it to reset. You have these distinguished bands that are associated with like W equals 0, 1, 2. And then as P increases, they become distorted and start to merge. And basically the reservoir absorbs them, gobbles them up one by one until all the eigenvalues are just, like eventually everything becomes like fully mixed. And you just have like a single peak. Right. And so we can actually compute or analytically derive this picture of, assigning the eigenvalues into successive buckets, where basically the bands of the eigenvalues, they keep this Marchenko-Pasteur distribution, but there's just this shift to the mean eigenvalue that you can calculate within first order perturbation theory. And doing that, you actually get very good results with the numerics. So here what I'm showing is like as a function of P, the minus log of the eigenvalue, and the sort of the light shaded regions are like the intervals of eigenvalues within that band. And then the dashed curve is like this ansatz for what the mean eigenvalue should be in that band. And there's pretty good agreement even through the transition, although we only really have control over this like away from the transition. So another consequence of this analysis is that we can argue like what actually changes between canonical and microcanonical. So they have a transition at the same spot, like still this hashing bound, but the transition gets more rounded out in the canonical ensemble. You know, if you want to assign like critical exponents or something, you would say that like the finite size scaling gives you this nu equals 2. But basically all that is just there's, right, I'm no longer picking out a specific weight. I have this distribution over weights, and that distribution has a width that scales like square root the system size. And so I can get a scaling collapse if I plot it versus p minus pc times square root n. Yeah, anytime I see a crossing, I have to do a scaling collapse. It's just in my blood. So I was happy that this one worked out nicely. Right, okay. With my remaining time, which I think I have a bit of time, I'm going to tell you what happens when we go past the hashing bound. Right, so, yeah, so, right. So as I described, above the hashing bound, the reason why error correction fails is because your typical error weight is lying inside this polluted reservoir. And like, you can't decode that. However, at that point, there still are these, at that point, there's still some part of the spectrum that is like well distinguished from this reservoir, right? Like all of the bands don't, like if in that animation, they're sort of getting sucked up one by one. So sort of the lower lying bands are potentially still have something that you could salvage. So like the unpolluted part. A very extreme case of this would be, let us post-select on returning to the code space. Or if you will, if this was like a stabilizer code, we would say, you know, I'm going to measure a zero syndrome and throw everything else away. And that strategy works up to a detection threshold. So we have this error correction threshold at the hashing bound. But if we throw everything away except for the zero syndrome, that will work up to a much higher rate. Eventually it will fail because even post-selecting on zero syndrome, there's a higher probability that it just was like some other like logical error that it was just undetectable. And so in the case of like a 0-rate qubit code, this detection threshold is at 1/2. I want to give a maybe slightly more detail on how this 1/2 comes about from a very quick and dirty argument. By thinking of the detection threshold as coming from just looking at the leading eigenvalue of the spectrum. The ansatz for the leading eigenvalues takes this rather simple form. Basically, there's some probability that you have no error. That's 1 minus p to the power n. And then there's another probability that you had an error, but then like the random state that you got has some overlap with your initial code space. So you sort of leak back into the code space. And basically setting these two things equal, so like this is like the good thing, and this is the bad thing. Setting them equal occurs at p is 1/2, or for k is order 1. Right. You can actually do better than this perturbative ansatz. You can actually calculate this exactly, but I think this sort of gives you the picture, and it's nice to see that things sort of hang together. Yeah, so you can also do numerics. You see that this transition is, again, only width of order 1 error, which you can understand as being, it's only coming from one band, right? We've post-selected onto the lowest band, so there's none of that broadening anymore. For the experts in the audience, well, everyone's an expert, but for the experts on this topic in the audience, I would note that you can get the same result using either quantum McWilliams identities or also using Weingarten calculus. It's sort of a very rich sort of subfield of looking at these transitions in terms of like high to low temperature dualities. So ask me about that after my talk if you're interested in it. All right, so I showed you like an extreme case, but what about in between these two thresholds? So we have this hashing threshold and the detection threshold. And so I'm going to tell you two different ways that you can sort of tune between them. The first way is I'll call microcanonical, and it's going to be, let me just project onto the subspace that's spanned by states that could, like any state acted, like a code state acted upon by up to weight, or acted upon by weight W error. So like you imagine your code space, you act with all possible weight W errors that define some other subspace. Let's project onto that. And a very similar argument to the one I showed on the previous slide gives you this curve here, this blue curve. So basically says, as you project onto like lower and lower W, you get a higher and higher threshold, interpolating between this hashing bound here and detection threshold here. The numbers here are for like qubit codes with 0 rate, but you can write down the formulas for more general case. Right, so this sort of is interpolating between the two. Another thing that you can do, which might seem a bit odd, but I'll motivate it on the next slide, is you can take this noisy mixed state, rho tilde, reweight it, by which I mean you basically take its spectrum and you reweight the eigenvalues by a power of alpha, and then you have to renormalize it by this trace. And I'll call this state sigma. And you can then look at the threshold of this guy. If you translate that threshold into like as a function of W, like so basically this reweighting sort of reweights what the typical error is in your spectrum, like what's dominating your spectrum. And then if you look at where the transition occurs and ask what is the weight there, it's this W star, and it gives you this red curve here. So the thing I want to emphasize on this slide is that these two different ways of doing some sort of form of post-selection, they both interpolate between the same extremes, the hashing bound and the detection threshold, but there is like an intermediate regime in between them. And if you'll indulge me, I would say that this is a sort of a manifestation of the inequivalence of the microcanonical and canonical ensembles, which is sort of kosher here because we don't have like a local spin model. It's like an all-to-all coupling thing. So they're allowed to be inequivalent. I want to give a little bit more detail on what this canonical reweight means, like, and why did we come up with it. And the reason is that in a certain segment of the population, there's been interest in these Renyi transitions, where basically people, instead of looking at the von Neumann entropy, they look at this alpha Renyi entropy, defined as this. The reason why people look at these is because they're very conducive to, say, like a statistical mechanics analysis of these transitions. And then usually what people do is they'll derive a bunch of stat-mech models as a function of alpha, and then they'll say, okay, yeah, and if you take the replica limit, alpha goes to 1, then you recover the true coding threshold. But what they don't provide is like an actual information theoretic interpretation of like what these higher Renyi thresholds actually are. Like there's some singularity in the entanglement structure, but like what does it mean for like say decoding? And what I'm going to argue is that sort of one information theoretic interpretation that you can give it is that it's this Renyi transition is really a transition in like a true coding transition, so like von Neumann threshold in this post-selected or reweighted density matrix. Actually, I'm going to tell you about sort of two ways that you can give this an information theoretic interpretation. So the first is very simple. It's just that you can sort of define this reweight in terms of like applying some POVM, and the probability that you will like accept that state, like so that you will not reject it, is basically it's a function of this or exponential of the Renyi entropy. There's also this minus of the Renyi infinity, but that has a singularity later, so you don't really have to worry about it. The point is just that if the alpha Renyi entropy has a singularity at some p, then this post-selection probability will also be non-analytic at that transition. It will basically change from scaling like in one way with system size to scaling a different way. I mean, I should emphasize that, right, like we're doing this post-selection, it's always gonna be like impractical in the sense of like, you're gonna have like an exponential cost for post-selecting, but what I'm claiming is that that cost, like how it scales with system size, has a change, like a sharp change at this transition. So basically the reason how this comes about is that like below some PC alpha, this alpha Renyi entropy is just going to be dominated by like these correctable errors at some weight W star, which you can calculate. And then above PC alpha, it will just saturate, like the entropy will just saturate at the system size, minus K. And it will just be governed by these non-correctable errors. The second interpretation is that, okay, so we see that there's like some transition in the post-selection acceptance probability, but now if we, also wanted to say that for Haar codes, we can calculate what this is, and it's sort of a generalized hashing bound where you just replace the classical Shannon entropy with this Renyi version of it. Right, yeah, okay. The second way that this transition manifests is if now condition on post-selection succeeding, or like we've done this reweight, now we look at this post-selected state. That post-selected state has a coding threshold, like as probed by the coherent information, at this PC alpha. So basically below PC alpha, the post-selected state will be entangled with the reference, and then beyond that, the information will be lost to the environment. Right, and you can see this in the panel on the right-hand side is showing this coherent information on the post-selected state for alpha is 2, and it has a crossing at the analytical value that would be predicted by the equation on the previous slide. Another plug for, you can also get this one from a quantum McWilliams identity, sort of a special thing. You can also get the finite size scaling from quantum McWilliams identity. But this, I'm just showing the numerics. And then the other point I want to make is that as you increase alpha, you can interpret that as biasing the post-selected state towards the more correctable errors or the more correctable bands. And so that's going to lead to sort of a monotonic trend in PC alpha as a function of alpha. So again, this is sort of just a different way of plotting what I showed a few slides ago, now as a function of alpha instead of W, where basically you can see that it interpolates between hashing bound and then asymptotes towards the detection threshold. And that's 2 there, marked as a star. Right, yeah, okay, yeah, so that's enough about the Renyis. Now I want to provide some outlook. Yeah, so, okay. So the big idea that I hope I conveyed is that although Haar-random codes are sort of, in a sense, more random than stabilizer codes, they have less structure in them, they actually have the same threshold. This maybe goes against the intuition that like, if you remove some of the structure, you might get like a better code. In this case, you don't. You still have the same threshold. It's an open question, like, so what are the sufficient conditions for an ensemble to have, like, to saturate this bound? Like, you know, okay, you can say that a random stabilizer code and a Haar-random code are sort of similar because, you know, Clifford group is a 2 design or a 3 design. So is that enough? Like, it's unclear to us right now. So that's one question. Another thing is that I told you about how post-selection sort of provides an interpretation for a sequence of mixed state phase transitions that you can get past this hashing bound. Some things that we've been thinking about lately is sort of to what extent that intuition about like the sort of band structure and how we're able to like reweight it, to what extent does that survive in like say a degenerate stabilizer code? So there have been some sort of suggestive results suggesting that there's a this monotonic trend with alpha in say like toric code, but our reasoning like for why that happens, like basically this idea that you're just reweighting towards more correctable errors, doesn't like immediately go through for like a highly degenerate code like toric code, whose band structure is like a lot more complicated. And then some additional things that we've been thinking about a little bit is there's a connection to approximate error correction in these sort of eigenstate codes. So instead of having like totally Haar-random, you imagine you form your code words from like the eigenstates of some chaotic Hamiltonian. There's also been this recent work looking at replacing the Haar ensemble with this thing called the Scrooge ensemble, which I just love. So I had to put it on here because it's just great. Because it's stingy, that's why it's called that. And so that one could imagine making like a Scrooge random code or something of that sort as a way to reintroduce structure, or you could add like certain symmetries basically. And then there is the question of whether, so there's like this, decoder for like say erasure errors on a Haar-random code, this Yoshida-Kataev decoder for like a black hole basically. It's unclear whether this could be adapted for like our model. Like so there's a, you can construct a decoder, but like, but it's not like efficient at all. And there's a question of, could you do a little bit better than like the current decoder that's known? Yeah, and then with that, I just want to thank all the people that we spoke to while making this paper, and thank you all for listening, and again, refer you to this archive posting for more details. Thanks. Yeah.
Thanks so much for a great talk, Chris. Do we have any questions? Andrew.
Thanks very much. That was really interesting. So just in the plot of the decoder threshold, where was that threshold located in your numerics? Like I might have been hallucinating, but it didn't look like it was exactly, not this one, the standard decoder.
I think it was, sorry, I went past it. This one?
Yes. So no.
Oh, the one that's at a half?
The one that's at a half, but it looked like it was at more than a half. This one.
Oh,
yeah,
yeah. That's finite size effect. Yeah, the crossing looks like it's a little bit past a half, but we're only going up to system size 13. Like we know, like there's theoretical, like it actually has to be at a half based on this identity. But you're right that on the system sizes that are accessible, it looks like it's slightly past that.
Okay. Right. So your finite size ansatz is actually, yeah, like because it looks like the finite size effects are under good control, but yeah, they're still they're under control, but they've deterministically shifted.
Yeah, I think that's a way to explain it. Yeah. No, it's not. Well, yeah, no, it's not. Right. It would be if this was like toric code, and I was looking at the Renyi infinity for that. Then it would be clean easy model, literally. Here, no. I think the best intuition for why nu is 1 is because that's sort of like as narrow as it could be, because you can think of that as being like of order 1 error width, right? Because you would rescale like p minus pc times n. And that's just because there's only like one band contributing. So like, if you believe like this Marchenko-Pasteur thing, then it sort of has to be nu equals 1. But you can actually get this one like exactly by doing some Weingarten magic. And so, yeah, so like, it is, yeah, it's not Ising, but it is nu equals 1.
So when you're talking about post-selection, you're saying you're selecting a particular micro-canonical ensemble, right? So you're just selecting.
So it's not actually the same as doing like the microcanonical channel, because it's Yeah, you're applying the whole channel, and then you're post-selecting on the subspace that's spanned by like the microcanonical. And so that has contributions from other errors could have occurred and landed you on that subspace. So that's why it's, it depends on, yeah.
So this is where the logical component comes from.
Yeah, basically. Right, because you can imagine if I said I post-selected on actually 0 error occurring, then I would never have a threshold, right? But if I post-select on the subspace that's spanned by 0 error, then it could have come from a logical undetectable error, which is what happens at a half.
Yeah, Tom?
Yeah, so you talked about this post-selection where you have 0 error. Could you also make sense of like post-selecting on some expectation value of like some effective stabilizers that's like between sort of 0 and maximum? And like what would it mean? Like I guess you kind of have some stabilizers by pushing the original Z errors through the random unitary. And then if you had some errors, you could look at like how much expectation value they have.
Yeah, we haven't thought about that. I guess you're sort of, maybe like an equivalent would be like if I had a stabilizer code, you're like sort of these, you can post-select on say like the number of stabilizers that's violated or something. Like with some, yeah. Yeah, we haven't really thought about that. I'm not sure how that would work for like Haar-random, but there might be a way to conceptualize it.
Thank you, that was very interesting. Lots of new stuff to learn. So I'm particularly interested in the eigenvalue distributions of the canonical ensemble. Like how much of this is like specific to your model and like how much is like generalized?
Okay, so something I can show you. Okay, so it's not actually, okay. Bonus slide. Let me get to it. Where'd this go? Oh, I'm not on the bonus slides yet. Okay. Okay, yeah. A question you can ask is like, what happens if I have a stabilizer code? How does the spectrum look in that case? In that case, you can basically actually describe the spectrum, like every eigenvalue just corresponds to like a logical class probability. So in particular, the eigenvalues of rho tilde q are just like literally proportional to the probability of getting that syndrome. And rho tilde rq, it's like for each syndrome, right, there's like different logical cosets, right? And you can look at this in like, say, an example of some like very small code. So for example, 7-qubit Steen code. In this case, you don't have any broadening. You basically get completely sort of flat bands in the sense of there's this lowest band, which just has one eigenvalue, and that's like the one corresponding to 0 error or 0 syndrome. Then there's the next band, which corresponds to all possible, there's 21 different syndromes that come from one error. And it's non-degenerate, so yeah, at that level. So it turns out those all have the same probability. And then there's the highest band, which is just the remaining errors, and those also all have the same probability. Then if you look at the spectrum of RQ, basically each of these curves gets split into 4, but some of them are degenerate. So, okay, so I would say from this, like, you don't have the same distribution within a band, but like you do have a clear separation. A more complicated case is like 9-qubit Shor code. Here you can sort of imagine that you're getting some sort of like band dispersion because not all, say, weight 1 errors are equivalent. Or what I mean is like some of them are more dangerous than others, and also you get like some of them are related by stabilizers. So you can sort of think of this as being like band 0, band 1, band 2 reservoir, but they're sort of like separated a little bit. So this is just to say that some aspects of the structure do survive, like under like adding a lot more structure to the codes, but things get a lot more involved. Like certainly the very simple like Marchenko-Pastor thing will not like survive to like more structured codes.
Can I ask a clarifying question on that? In this local stabilizer code context, when you call it a band, what is the...
Yes. What I mean here is just like the sort of, okay, like, yeah, they're the eigenvalues that are sort of like close together. So actually, what I'm labeling here is there's actually like, you know, say in this case, 3 degenerate, I don't know why I'm using my finger, I have this. Like there's like 3 degenerate eigenvalues in here. And then like in the green one, there's like 18. So you can think of that as being like, if you think of the eigenvalue as being like an energy, it's like a band of energy that in this case is like, you know, completely degenerate in the sense of like, or completely flat in the sense of like all the eigenvalues in that band are the same. That's what I sort of mean. And like in this case, what I'm arguing is that like these two are sort of like belong to the same band in the sense of like they're sort of following the same form. Like if you look at the leading contribution, it's just like these ones occur with probability like proportional to p, and then like these two proportional to like p squared, and so on. So in that sense, they're sort of like the same band.
Can you still in this context build from this microcanonical ensemble to the canonical in the same way?
Yeah, so I should mention that these plots are like hot off the press of, we just started looking at this as in response to a referee. So one thing maybe I should say is that like here I'm not actually showing any transition because I'm just giving you a single system size. Like, I'm not scaling anything up. But you can certainly ask about like transitions in like families of these codes, and then yeah, probably there actually the microcanonical to canonical would follow even more immediately because you have like a local spin model or something. So there they should actually directly correspond. But we haven't really thought about this in too much detail yet.
Thanks for a great talk. You sort of invited us at the beginning to ask you about the relationship with that simultaneous.
So that paper was, in our language, I would say it was focusing on the microcanonical ensemble. So if you looked at the title of it, it's actually about quantum Hamming bound, or approximately quantum Hamming bound. So what they're looking at is you fix like the total number of errors, which in our case is the same as saying like you fix the error weight, because that like gives you some set of errors. And when they're able to prove is that you get this like approximate error correction, or like, you know, the error is like decaying exponentially or whatever, as long as the total number of errors is below this like hashing weight, or like basically below the total size of the Hilbert space. There's some more direct connections you can make about basically like the sort of the Marchenko-Pastor distribution, and some proofs they have about like they construct this isometry. Well, it's actually not an isometry, but they can bound like the eigenvalues of certain things, similar to like what we did. I would say the biggest difference between the papers is that theirs has proofs and theorems, and ours is not. It's written in a very much different style. So computer scientists versus physicists, I guess. But a lot of the basic context, that aspect is very similar, although they don't talk at all about like the post-selection and stuff like that. So read our paper first.
So I guess your model is like kind of non-dynamic in some sense, right? You just apply like one layer of placement. Is there some sort of extension to like a dynamic model that would make sense, or that would be interesting?
Yeah, no, that's a good question. I guess, yeah, we haven't really thought of it because we're not actually imagining like doing like noisy syndrome measurements because we don't even really have a decoder. So yeah, I would have to, I think for that, like you would really want to like have like some, you know, like construct some actual like decoder or something to, but there might be a way to extend it, but I haven't really thought about it carefully yet.
So a quick clarifying question. So when you had this nice animation of your different bands as you increase your error, did it show that all these bands merge to some big mixed state at the exact same time? Or is there some sort of like...
No, so basically what happens is, okay, so I can show you like, I have the sort of the frozen version of it right here. you can see like at this point, let's focus on like RQ. Basically, there's a tiny quote unquote band here that just has like one eigenvalue. Then there's this like mini one here, this guy here, and at this point, at like this value of P, this other band here has like been partially merged to the reservoir. So it's already been sucked in, and then like this guy will go next, and then this guy will go. So they sort of like successively get swallowed up. So like if you go to the animation, you can see they start to merge. But are you asking about the two different panels, or?
No, yeah, that's great. So is that something you would sort of, why do you expect that from the model for them to sort of
Well,
work
because
in that order?
because I mean like the one starts like closer, right? So I mean like they start out separated, you know, and then like they get this correction, like they get this shift, but like but like successively they get closer to basically the reservoir. Yeah.